So we are discussing questions based on the concepts of magnetism. So here the question is the substance used for preparing electromagnesis. So we have options available here. You can view the options: soft iron, steel, nickel, and copper. So correct answer will be soft iron because of low retentivity. As the current is switched off, the magnetism is removed instantaneously. So, question was asking about the substance used for preparing electromagnets. Preparing electromagnets use soft iron. Why? Why? Reason is why? Because of low retentivity. Okay. So you need to take care of this concept because questions usually asks in examinations, and there we do some types of mistakes. You do some types of mistakes. So take care of low retentivity. Because the option will also play with you high retentivity. Okay, they will give you high retentivity. Okay, so don't be confused there. So try to use that. You need to take care of the concept is that low retentivity. Is this clear? Okay, so we are moving a little bit fastly. So next question we are moving with B square by mu naught has the unit of, so B square has the unit of, we have options: energy, energy density, potential, and capacity. So already all of you know that B square by mu naught is what? Weber per meter square whole square divided by, so you can don't do like this. Okay, so I'm saying this, yeah. So keep this relation finally in your brain, that this one. Okay, so ampere square by meter square. Okay, basically it's what a unit of energy density, unit of energy density. Okay, so all of you already know the formula for energy density is what? Energy density formula is what? B square by 2 mu naught. B square by 2 mu naught. So I'm talking about B square by mu naught. So obviously this is energy density. So don't get confused over here. So next we are moving for next question. So this will be like this. Okay, so ampere square, meter square. So you can solve it like this. Yeah. So yeah. Next questions we are moving with Earth magnetic field always has a horizontal component except at, okay. The question is talking about Earth has a horizontal magnetic field, okay, except at equator. Magnetic pole at latitude 60 at inclination 60 degrees. So correct answer will be at the pole. What is angle of dip is what? 90 degree. Okay, at pole angle of dip is 90 degrees. If you take a horizontal component is what? I cos theta. All of you this formula. So horizontal component is I cos theta. Obviously, Earth is like this. Okay, so if you see horizontal component at pole will be what? Zero. Okay, because the angle will be so 90 degrees. So this is zero. So what will be correct answer? So magnetic pole. We'll go with magnetic pole. Next, we are moving for next questions. Next question, we have the core of electromagnetic made up of soft iron because the susceptibility of soft iron is very high. Porosity of soft iron is very low. So this options we have. So I'm giving you the options. Yes. So I'm giving you the options. So this, and this. So you can go with the options. What will be correct answer? The correct answer will be the third. Both A and B is correct. Why? Because soft iron. If you see the soft iron has a low retentivity and low porosity, high permeability, and high susceptibility. So mu equals to mu naught of 1 plus x. And all of you should know this formula. If you don't know, so you should know. Okay, so your class teacher already taught all this concept in your. Okay, so if you don't, so you can add in your notes 1 plus x of m. Mu equals to mu naught 1 plus x of m. Okay, so susceptibility here x of m I'm saying for susceptibility. Okay, so mu of mu naught of 1 plus susceptibility. So take care of this concept in your brain. Okay, so definitely you can do these questions. Okay, yeah. So here the core of electromagnet made of soft iron because of the susceptibility of soft iron is very high. Susceptibility of soft iron is very high. Correct up. And coercivity of soft iron is very low. I already taught you this concept here. Low coercivity, high permeability, high susceptibility, and low retentivity. So next we are moving for next questions. Okay, next questions we have out of the substances statement given below, the correct statement is soft iron conducts electricity. Soft iron is magnetic material. The soft iron is used for permanent magnet. Soft iron is used as electromagnets. Answer we have these options. So here if you see the answer will be what? For soft iron is a conductor of electricity and it is a force magnetic substances it used for preparation of electromagnets. Okay, so you need to take care of this thing in your brain. The soft iron is a conductor of electricity, a conductor of electricity, and it is a four magnetic substances. It is used for preparation of electromagnets. Okay, so we'll go with answer T4. Next question, so we are moving with. So next question, magnetic meridian is the point, a line along east-west vertical plane, horizontal plane. So here we have options. So here we have the answer will be what? Third, that is vertical line. What I'm saying, it is vertical line passing through the magnetic north and south pole of the earth. Okay. So what is magnetic meridian? Passing through the magnetic north and magnetic south of the pole. Okay. So there is, we are not talking about geographic south or geographic north. We are talking about magnetic north or magnetic south. So if the line is passing through magnetic lines or vertical planes, what is we are talking about vertical planes that is passing through the magnetic north and magnetic south pole of the earth. Okay. So yeah. So next question we're moving ahead. Okay, next question we have, when a bar magnet falls in a metal cylinder on the vertical axis, the acceleration of the magnet is basically what's the question? We have a bar magnet falls in a metal cylinder. So this is a metal cylinder. So basically bar magnet is falling inside it. Okay, so vertical axis, the acceleration of the magnet. This is very question for IIT JEE. This is very famous question for IIT JEE. So all of you should know. So this question is asked many times in many different examinations. So correct answer will be less than G. Why? Because the induced magnetic flux in the cylinder oppose the motion of the magnet, so it moves with an acceleration less than G. So you should know this concept. I hope, see, question is so easy. If you know the concept and question is so easy. If you don't know, it will be very difficult. You will get confused over what question you're asking. So it becomes very difficult to understand the questions. If you know, then you can do it easily, faster. Yeah. Before that, you have to take care of your classroom. Okay, wherever you are taking classes. So that's very important to take the classes. What your teacher is teaching over there. Yeah. Next question: the magnitude of magnetic moment of a semicircular magnet of a radius r and pole distance m is. So magnetic moment is very easy questions. It's very easy questions. Semi-circular magnet. So we have a magnetic moment of semi-circular magnet. We have semi-circular magnet, and their radius is what r. And pole distance, we are talking about pole distance. Pole distance is m. This is pole distance m. This is very easy questions. If you know the concept, you can do it in this question fastly. So what will be correct answer? So correct answer will be what? Okay, correct answer will be 2mr. So correct answer will go with option number 2. So this is very important concept. All of you should know. See, basically what we are connecting initial point and final point, and then magnetic moment. All of you know magnetic moment basically what? Magnetic moment is what? Pole strength into length. Basically, take care of this concept in your relation. Some of the students remember this relation as m into 2l. But usually, what I say, advise the student, don't remember like this. If you get confused, so like if you remember the formula like dipole, okay, in the electrostatics. So try to remember the formula in the form of m into l. Here L is what 2r. So what is L is what 2r. Here L is what 2r. So take care of this concept. Definitely you can beat the questions. Yeah. So yeah. Next question. We are moving ahead. Next question we have. So a steel wire of length L has a magnetic moment M, and then it's bent into semicircular arc. Then the new magnetic moment of the arc is. So yeah, question asking us the new magnetic moment of the arc. A steel wire of length L. This is length L, a steel wire. And the magnetic moment of this wire is capital M. Then it is bent into semicircular arc. Then the new magnetic moment is, again, this is very questions, very good questions. Okay, if you know the basics, then you can do this question very easily. So basically, what formula we are applying for magnetic moment? 2m sine theta by 2 divided by theta. 2m sine theta by 2 divided by theta. 2m sine theta by 2 divided by theta. So if you have a wire whose magnetic moment is m, already given in the questions. So basically, what is the angle? If you convert this into, okay, if you convert this into what? If you convert this into what? Tell me what? Okay, bending form. So what is the angle here? Okay, pi by 2. Angle is what? Pi by 2. Angle is what? Pi by 2. 90-degree angle is forming. So this will be what? Okay, and you see this is basically this is what pi by 2 and all. So two and theta by 2 divided by. So I'm actually basically what I'm saying here. This is 2m sine theta by 2 and all. So 2m sine theta by 2 is here. Am I right? So see, what is sine pi 1? What is sine pi 1? Here basically it should be theta by 2 to sine theta by 2 divided by theta by 2. 2 sine theta by 2, we write this formula is like this 2m sine theta. So in the terms, 2m sine theta by 2 theta by 2. So basically, uh, and this is we are using here. Okay. So I will do. We need correction here. So basically leave it right now. So basically, answer will come 2 m by pi. Okay. Answer will be 2 m by pi. Okay. So answer will come 2 m by pi. So you need to take care this concept in your brain. This is very important questions. Okay. So if you know, then you can do these questions. Okay. Yeah. Next question, we are moving ahead. Next question is two bar magnet of different magnetic length have equal moment. Then the pole strength is. The question is asking the two bar magnet of different magnetic length have equal moments. Then the pole strength is. The question is asking about pole strength. Okay. So equal for both the magnets, less for shorter magnet, more for longer magnet, more for shorter magnet. So what is M1 equals to M2? So M1, so question have already given that both have equal magnetic moment. Both have equal moments means M1 equals to M2. So basically what is happening? M1 into 2 L1. Yes. So M3 into 2 L2. So from here, what we are observing this, and so pole strength of shorter magnet. Okay. Basically, what we are observing, M1 is inversely proportional to length. So we can also say M is inversely proportional of length. Okay. So M is inversely proportional length. So if the length of, is more, pole strength should be less. And if length is less, so pole strength should be more. So pole strength is more for shorter magnet. Pole strength is more for shorter magnet. So I hope all of you understood for questions. And next we are moving with next questions. So if a bar magnet M is bent into at its midpoint, so that angle between the two parts is 120 degree. Now the magnetic moment of the magnet now is okay. So basically what is happening, a magnet of magnetic moment M. So there is a magnet whose magnetic moment is M. We are bent into at its midpoint. So when midpoints, so that angle between two parts is 120 degree. This is 120 degree. Again, this is very good question. So if you know the concept, then only you can do this question asking you the net magnetic moment. Net magnetic moment. Again, apply this formula M sine theta by 2. M dash is M sine theta by 2. So what is happening here? 120 degree. Now angle is what? 120 degrees. So sine 60 degrees. So this will basically it will become what? So root 3 by 2. So like this we can go. So take care of this formula. M dash is basically what? M sine theta by 2. M dash is what? M sine theta by 2. M dash is M sine theta by 2. Next, we are moving ahead for next question. So Joule per Tesla is the unit of torque per a unit twist, magnetic moment of the magnet, pole strength, work done per unit pole. So question is what we all of you know, and basically W means U is M dot V. So that is unit of W is Joule. Okay, unit of W is Joule. So unit of B is Tesla. So if you divide, okay, Joule, question is talking about Joule per Tesla. So if you see Joule and B is Tesla, so it will become magnetic moment. Okay, it will become magnetic moment of the magnet. Okay, so magnetic moment of the magnet. So it's a magnetic moment of the magnet. Okay, yeah. So next question we are moving it. So conceptual questions. If you know then only you can do this question. Next question we are moving it when a bar magnet is heated, its magnetic moment. We are talking about it's very rare, easy questions. Okay, this is okay. Board examination based questions. So basic understanding requires for solving this question. So we are talking about when a bar magnet is heated. So it's a magnetic moment will decrease, heated, then arrangement of atomic magnets is disturbed. So because of that, arrangement of atomic strength is atomic magnet disturbed. Due to this, the pole strength of the magnet decreases, and hence its magnetic moment decreases. That is M equals to 2 L into M. So I hope all of you understood the concepts. Next questions we are moving ahead. Next question we have Newton meter cube per Weber is the unit of magnetic flux, magnetic moment, magnetic induction, pole strength. So all of you should know that Newton meter cube divided per Weber is basically what? Newton is for what? Force. Newton is for force. Meter cube is for volume, and Weber is for flux. Weber is for what? Flux. Weber is for what? Flux. So if you solve it, so flux is B into A. Flux is what? B into A. Flux I'm writing B into A and force. And if you say V by A is what? L. So this is what? F into L by B. So all of you already know the dimension of this. So just try to put the dimension, and once we solve it, so we are getting AL2. AL2. So this is the unit of what? Ampere meter square. Basically, it's what? Basically, ampere meter square. And what is ampere meter square? Magnetic moment. What is magnetic moment? Another formula for magnetic moment is I into A. Another formula for magnetic moment is I into A. So this is what? Ampere, and this is what? Meter square. If you understood the questions, you can do this question easily. Very easy to do. And next question, we are moving ahead. three identical bar magnetic submagnetic moment M are arranged in the form of an equilateral triangle such that the unlike poles are contact. Okay. So yeah, so it's okay. So basically we are forming a triangle like this, equilateral triangle using okay, bar magnet M, okay, are arranged in the form of equilateral such that unlike poles are contact. Resultant magnetic moment is question talking about, okay, question talking about resultant magnetic moment. So from here, resulting magnetic moment will be what? If you observe the figure, so we are arranging this in unlike, okay, unlike poles, north, south, north, south, okay, north, south. So we know inside the magnet, it's the direction south to north, south to north, south to north, south to north. So net, so if you know if you understand basic understanding of vectors, so net will be what? Zero. So if you have a basic understanding of vectors, so net will be what? Zero, or directly you can do directly, no issue in it. But if you want to go manually, so you can do like this. So what do you get? This is going to be zero. Basically, what I have done, I have taken the component of this magnet, okay, this direction, okay, and on the similar fashion, okay, I took the direction of this, okay, here direction of this magnetic moment in this direction, m cos theta. So what we are observing, m cos theta will balance m cos theta, and this m sin theta will balance m sin theta, and so on. You can compare. You can give so many reasons, so many ways to explain that this is zero. No issue in it. Okay, so now we are moving ahead. Next question: when n identical magnets arranged in the form of closed polygons with unlike poles near air, so the resultant magnetic moment is zero. The question is talking about the resultant magnetic moment is zero. Next, if one magnet is removed from our resultant magnetic moment becomes capital M. If one magnet is reversed in the polygon, the resultant magnetic moment of the combination becomes 2M. So we have options A, B, C correct, A, B, and B are correct, and C is wrong, only A is correct, only A, B, C is wrong. So basically what's happening, see, this is the magnet, okay. So basically what we are doing as south, north, okay. So how many sides we took over here, polygon? So for polygon, we took here 6, okay. So 6 sides, 1, 2, 3, 4, 5, and 6. So if you see, this is south, north, this is what? Again, south, north, south, north, south, north, south, north, south, north. So if you see south, north, and this way, okay, this is south, north, okay. So we took 6 polygon in order. Again, you can apply the same concept and result is going to be 0. So what do you see? The magnetic moment because of 1, 4, because of 1, 4, 2, 5, and 3, 6 are opposite. Okay. So I'm erasing it so that it will look clearer. So 1, 4, I'm talking about 1, 4. If you see 1 and 4, it's opposite in direction. Opposite in direction. See, south to north here, south to north this direction here, south to north this direction. Because of this magnetic moment will be opposite, so this will cancel each other. Do you agree? 1 to 4 and 1 and 4 will cancel each other. If you come to 2 and 5, so 2 and 5 similar fashion, 2 and 5 will cancel each other. Similar fashion 3 and 6 will cancel each other. Result is 0. So magnetic moment of 1, 4 and 2, 5 are opposite, so they come out, but magnetic moment of S remain. So magnetic moment of S remains. So the resultant will be what? M. So resultant magnetic moment will be capital of M. So if you understood the concepts, next process we are moving ahead. So like this, okay, you can see M plus M will add it. So magnetic moment of 1, 4 to 5 are opposite, they come out, but the magnetic moment of 3 and 6 are in same direction. If you see the direction of 3 and 6, okay, 3 and 6 with the direction of 3 and 6. Why the direction is same? Why the direction is same? You can understand this is okay, north, south, and this is north. So okay, so this is the direction. Because of that, okay, the direction is coming same. So if the direction is coming same, so resultant will be 2. And if you think on this question, this is a deep question, so you can do this question easily. Next question we are moving with SI unit of magnetic flux is very easy and doable question. So what is the answer? Weber. SI unit of magnetic flux is Weber. So all of you should know. Next question, we are moving dimensional formula for magnetic field of induction. So question I asking dimensional formula. So force is LB. So from here you can find out the dimension of B. So you can solve it and you will get the dimension for magnetic field of induction. That will be MT minus 2 I minus 1. Next also we are moving with the magnetic induction due to magnetic pole. The point is capital B. If the distance of the point is double, then magnetic field will. It's very easy questions. You can do it. Okay, easily this question. So magnetic induction due to magnetic pole at a field is B. So see this. If the distance of the point is double the magnetic induction due to magnetic pole at a point is. Basically, so this is what mu naught M. So this is basically what we are doing. So this is near to the point. So basically we are using the magnetic field will be what? K this relation. Use this relation K m by okay r square. Km by r square. You are using this relation. If you are using this relation, k is what, mu naught by 4 pi, mu naught by 4 pi, km by r square, km by r square. So on. You can do these questions. You can handle this question. So it's basically radius, opposite of radius, and answer will be come b by 4. Next question, we are moving ahead. Two bar magnets have the same magnetic moment but have different length. But if the still at the same distance on the equatorial lines are measured, the shorter magnet produces a stronger field, longer magnet produces this. So we have options. Both fields are equal. All the bar possible. So you can go this question once again, because two bar magnets have a same magnetic moment. So we have two bar magnets, both have same magnetic moment, but have different length. If the field at the same distance on the equatorial lines are measured, the shorter magnet produces stronger field, a longer magnet produces stronger field. Both fields are equal, and all the above are responsible. To solve this question, so see what I'm showing here. So basically, what is happening? Km by dq. Okay, so if you see the relation, okay, so basically what is coming here? So b is what? Okay, b is what? Okay, mu naught by 4 pi equatorial line. And we are not talking about axial. We are talking about equatorial. So what? M by r cube. Do you agree? Do you agree? So mu naught by 4 pi m by r cube on okay equatorial lines. Okay, on equatorial lines. Or in place of m, what can you say? M into 2l. M into 2l. A small m into 2l is the capital M. Do you agree? So if a small m into 2l is the capital M, so from here, what do you observe? B is proportional to a longer magnetic longer magnet produces. Okay. So what we are saying? So the simple relation equatorial lines of mirrors. So a longer magnet produces a stronger field. Can we say? Tell me. So this will be the answer. So now we are moving ahead. Next process we have the magnetic induction due to short bar magnet at a distance b from the center of the magnetic B. If the distance is double, then along the magnetic line, the magnetic induction will be. So magnetic induction due to short bar magnet at a distance d from the center of the magnetic B. So distance is double. So the question basically what you say, magnetic it must be proportional to dq. Do you agree? Magnetic field it must be proportional to dq. Magnetic field it must be proportional to dq. So do the problem here, so you can say it's easy questions. You can do this question very fastly and easily. So this is going to be B by 8. Next question, we have two isolated north pole. Each of pole is an M are kept at two centers, corner of A and B of an equilateral triangle of side D. So we have equilateral side. Okay, so we have equilateral side, equilateral triangle of side D and D and D. So two isolated north pole of each of the pole strength and each of the pole strength and kept at the two corner of A and B of equal triangles of side A. The resultant induction at the midpoint between the poles and side AB is 0, and this resultant induction at a point outside the poles on the line AB at a distance D from A or B is 5 by 4. This resultant is third corner is 0, and this. So what will be the correct answer? So I'm showing you the options. These options we have. So at midpoint, we are talking about at midpoint. So it will be what? Basically, what is happening at midpoint? So D becomes a D by 2. Do you agree? At the midpoint, the magnetic field D becomes a D by 2. Do you agree? So because its total length is D, so D by 2. So B will be what? B1 minus B2. B will be what? B1 minus B2. B will be what? B1 minus B2. Do you agree? So this so on. So you can solve this question. So you can okay at point C. So if you see B1 plus B2, mu naught by 4 pi m, and this D square plus D square, if you solve it, it will come like this. Okay. And at the third corner, if you solve this, will be coming like this. Okay. So you can solve it, you will get the answer. Answer will be coming like this. Okay. So this. So we are moving ahead. You can do this questions easily. So that so on you can solve this questions. Answer will come. Okay, like this. Okay. And answer key will be third. Next questions we are moving ahead. Next question we have a bar magnet is cut. A bar magnet is cut into two equal halves. So this we have bar magnet. We are cutting it into two equal halves. Plane parallel to the magnetic axis of the flowing physical quantities. The one which remains unchanged is. So if you are cutting the bar magnet into two equal parts, so what is going to be unchanged? What is going to be unchanged? First, the pole strength, magnetic moment, intensity, magnetism, moment. So what is happening? Pole strength of each piece is m by 2. So when you okay cut it, so pole strength of each magnet is going to be m by 2. The length of each piece is what? 2 by 2l. Means pole strength of each piece is m by 2. Length of each piece is 2l. So magnetic moment of each piece what? If we talk about magnetic moment, m by 2 into 2l. So volume which is what? M by 2. Volume which is what? B1 is M by B. Basically, B, we are talking about B by 2. The intensity of magnetization which volume will be what? Intensity is what? M by V. All we should know this relation. Intensity of magnetization is what? M by V. M by V. So intensity this is B by 2. The intensity of magnetization M by V. All of you should know this relation. Intensity of magnetization M by V. So from here, what you are observing, intensity is again coming M by V. It means I dash is equals to I, that will not change. If you talk about moment of inertia of each phase, so moment of inertia is going to be, okay, the moment of inertia is going to be what? Okay, the moment of inertia is going to be here, so ml square by 12, ml square by 12, and if you solve it, so what's happening? M dash, if you put M dash, L dash, okay, and okay, this one, 12, okay, so L dash is going to be L here we are using, so if you solve it, it is going to be like this. So on you can solve this question. Next question we are moving ahead. In case of bar magnet, lines of magnetic inductions. In case of bar magnet, lines of magnetic inductions start from the north pole and at the south pole. Run continuously through the bar. These easy questions. So see here, starting from inside south to north and outside north to south, like this. So run continuously through the bar magnet and outside, throughout the bar magnet and outside. Next question we are moving with magnetic lines of force are continuous, discontinuous. So magnetic lines of force are continuous. All of you know. Next question we have two total number of magnetic lines of force obtaining, originating or terminating on a point strength of M is. This is very easy and good question. So that is mu naught times of M. So mu naught lines are assumed to be associated with each unit pole. So if a body encloses a pole of strength M, so total lines of force inclined line with the body is mu naught times of M. Mu naught times of M. Total lines of force will be mu naught times of M. Next questions we are moving ahead. Next questions we have an isolated magnetic pole is an imagination. Isolated magnetic pole. Isolated magnetic pole. Imagination. This is made up of atom, made up of electron, exists only in space. So what is correct answer? Is an imagination. So an isolated magnetic pole does not exist and it is only an imagination. Next question we are moving with the lines of force of the bar magnets are parallel, straight, concentric circles, curved lines, and curved closed loops. So what is correct answer? So curved closed loops starting from north pole to south pole outside the magnet and from south pole to north pole inside the magnet. Okay. So the lines of force of bar magnets are curved closed loop. Next also we are moving where the electric and magnetic field differ in that the electric lines of force are closed curved while magnetic lines are not. Magnetic field lines are closed while electric lines are not. Electric lines of force can give direction of electric field while magnetic lines cannot. So what is correct answer? Magnetic field lines are closed while electric fields are not. This is very important. Good questions. If you know, then you can do this question very easily. So magnetic lines fields are closed, but electric lines are not. Magnetic lines are closed, but electric lines are not. Okay. If you know this question, you will do this question very easily. Next question, we are moving ahead. You can see this question. Next question, the following instrument is used to measure magnetic field. So to measure the magnetic field, thermometer, pyrometer, hygrometer, flux meter. What is the correct answer? Flux meter. So flux meter is used to measure magnetic field. Next question we are going with the property of alloying magnetic lines of force through material is relative permeability. The property of alloying magnetic lines of force through material is relative permeability, intensity of magnetization, susceptibility, permeability. So alloying magnetic lines of force through material is the permeability. If it is not alloying means that is, then you can take the concept of relative because you are putting some other mediums which will be obstructing the flow of magnetic lines. Next question we are moving ahead. Next question we have Coulomb's law in magnetism is applicable to find the force between only short magnets, only magnetic poles, only long magnets, both magnets and poles. So correct answer to only magnetic poles, and we all of us know that. What is the formula? So F is what like Coulomb's law. Mu naught by 4 pi m1 m2 by d square. Mu naught by 4 pi m1 m2 by d square. So this is the correct answer. Next one, the dimension formula for magnetic permeability is so all of you already see this formula right now that F is given of M1 M2 and E squared. So what do you observe here? Magnetic moment. Magnetic moment. Magnetic. So whole moment is what basically I into L from here. And So you can solve this. You can get the relation. You can get the relation. So this. So mu naught is going to be like this. All of you know force is M1 T minus 2. The mu naught is going to be this. Next question, remember if the distance between magnetic pole is double, the force between them is. So if the distance between magnetic pole is double, the force between them is. So what is your observing force is proportional to inversely proportional to d square. So obviously it will be 4 times, means reduced 4 times. Next question, we are moving on force between two magnetic poles when their pole distance and distance between them are both double. Both double. It's very easy question. Now you apply the formula and see what we are observing. It is going to be equal. Okay, unchanged. Next question, we are moving to the distance between two short bar magnets arranged for accelerates double the force between them is. By basically what we are talking about distance between two short bar magnet arranged coaxially is double. Okay, is double. So basically we are doubling the distance, then the force between them is. So you already know this is the formula for force distance between two short bar magnets arranged coaxially. So between short bar magnets, force is this formula mu naught by 4 pi 6 m1 m2 by d to the power 4. So this is the formula F is proportional to mu naught by 4 pi 6 m1 m2 6 m1 m2 divided by d to the power 4. So from here we are observing that F1 by F2 is proportional to F1 by F2 is proportional to d2 by d1 to the power 4. This is an important formula for JEE examinations. If you know that you can solve the questions only, otherwise you can't solve the questions. So basically what we are observing is the force is proportional to d2 by d1 power 4, d2 by d1 to the power 4. So F1 because of bar magnets, so because of magnets, we are not talking about force. This is not for force. This is for the because of bar magnets. Next question, so I'm moving ahead. So you can see you solve with this and you can come like this. Next question I'm solving. Two bar magnets are placed on a piece of cord which flows on water. The magnets are so placed that their axes are mutually perpendicular than the cord. Okay. So magnets are so placed that their axes are mutually perpendicular oscillates. So neither rotates nor oscillates. So this is the situation. So we are placing the magnets in such a way that the both are perpendicular. So you see the situation. So what's happening over here? So this is what you can see the figure. So what's happening? And so that's what is the torque due to magnet 1 is equals to opposite to the torque due to magnet 2. The torque because of both magnet is opposites and the internal forces do not rotate, internal torques do not rotate or oscillate the torque. Next question, we have a magnetic field produced and directed along y-axis. So there is a magnetic field which is produced and directed along y-axis. A magnetic placed along x-axis. The direction of torque on the magnetic. So magnetic field is produced, produced and directed along y-axis. This is magnetic field produced along y-axis and magnet is placed along x-axis. This is placed along x-axis because the direction of the torque on the magnetic. Question talking about the direction of torque on the magnetic. So basically, what is the formula for torque? So all of you know the torque will be along the z-axis. Why? Because it's xy plane. So torque is what x. So the torque is what basically what torque. Basic formula is torque is what m cross b. Torque is what m cross b. M cross b. So you see this is the direction of magnetic field and magnetic moment. This is direction of magnetic field. So the torque will be in the z direction. Okay. So you know the concept and you will solve this question. Otherwise, very difficult for you to solve the question. Next question, we're moving ahead. So if a bar magnet of magnetic moment capital M is suspended in a vertical uniform magnetic field, it is given an angular deflection with respect to equilibrium position. Then the restoring torque on the magnetic portion is talking about restoring torque. So you can see the figure and all this. So restoring torque is what all of you know the torque is what basically m cross b. So from here, what we are observing, we are giving the distance of x and x is coming here to L of sine theta. So basically, what x is coming to L of sine theta. So this is going to m v sine theta. Again, the same way. So no issue with that. And when we sine theta x was 2L, this is going to the correct answer. Next question, we have an environment in a magnetic moment m is placed in the magnetic field of induction. Field distance b, each pole experiences a force F. Then the distance between the south and north pole of the magnet, the measure inside it is. So we are talking about what we are talking about each force experiences force after the distances between the south and north pole of the magnet and measured inside it. We are talking about a distance, so you can see F is what m into b. All of you know this relation, you have to know. So F is what m into b. So m is what 2L into m. So what is m? What is m? What is m? M is what capital M by 2L. Small m is what capital M by 2L. So you see, and you can solve this relation. So F is what m by 2L into b. Because all these relations, this MBY, this is going to be the correct answer. Next question, we are moving data bar magnet cap fixed with its length parallel to the magnetic meridian and identical magnetic parallel to the these such that its center lies on the perpendicular bisector above. If the second magnet is free to move, then it will be translating motion and rotational motion. This is both translatory and rotational motion, vibrational motion only. So what you are observing, a magnet is capped, but fixed with its axis parallel to the magnetic meridian. Basically, we are keeping the magnet cap fixed with the length parallel to the magnetic meridian. We are keeping a magnet parallel to the magnet. This is magnetic meridian. This is a magnet. This is magnet. We are keeping parallel to it. An identical magnetic parallel to this such that its center lies on the perpendicular bisector of the board. So this center lies on the perpendicular bisector of the board. If second magnet is free to move, then it will translatory motion and rotational motion, both translatory rotational vibrational motions only. So again, this is good question. So okay, what is happening here? See, okay. So we are keeping the two magnets south, north, and this. So the magnet produce non-uniform magnetic field. So both have translatory and rotatory motion. Both have translatory and rotatory motion. So answer going to third. Next question, we are going with when a bar magnet suspended really non-uniform magnetic field. The correct testimony. Magnet experiences only rotatory motion. The magnet experiences only translatory motion. The magnet experiences both translatory and rotatory motion. Magnet experiences neither translatory nor rotatory motion. The correct answer is what? So the magnet is suspended in a non-uniform magnetic field. So magnet experiences both translatory and rotatory motion. Okay, when a bar magnet is suspended freely in a uniform magnetic field, the correct experiment is. So basically, what's happening over here when we are keeping the bar magnet suspended freely in a uniform magnetic field, the correct experiment is the magnetic field is only couple and undergoes only rotatory motions. The distance of the Spencer wires contractions of the maximum on the magnetic normal to the field and this. So what is see if you see the magnetic momentum is like this, so couple acts on the torque which rotates the magnetic field. This torque will be along the wire. Torque will be along the wire. Torque will be along the wire. The torque basically torque is what M plus B. M is heavy that it has 90-degree torque. The maximum that is MB. Next question we are going to C1, C2, C3, C3, 4 subcouples acting on a bar magnet so when placed in a uniform external field magnetic field so when the angle between its equatorial lines and the field direction is 30 degree, 45 degree, 60 degree, 90 degree. Respect to the correct sequence order. So basically, we have a couple acting on a bar magnet. This is very good question. If you know, then only confuse questions. Basically, C1 is couple sequence, couple C3 is couple C4 is couple. With the couples acting on a bar magnet. Acting on a bar magnet when placed in a uniform external field, magnetic field, when the angle between its equatorial line and the magnetic field direction 40 degree, 45 60 degree, 90 degree respectively, the correct conclusive order is. So we need to arrange these in coaxial orders. If you are arranging this one sequence, the correct answer will be this correct answer will go with the correct answer. Okay, see, we are going with correct answer with this is the correct answer. Or if you arrange order C4, C3, C2, and C1. Next question, if you see here, what I'm saying, see, couple is what basically M plus B torque. Torque is couple here. So C is what basically proportional to sin theta. If theta is more, couple will be more. Theta is less. If theta couple will be less. I'm using this concept and solving this question similarly. You can also solve the questions in the same manner. Next question, we are moving ahead. This is again good questions that null point on equatorial line of a bar magnet when the north pole of the magnet is pointing. This is north magnet pole, this is south pole magnetic B H and this is W and this is the magnetic this is direction. Here I'm assigning E for east and W for west. To understand this question, what's happening in this question, to solve this question, so what is something north towards north pole south should point north. So point north. Okay. So next question we're moving ahead. Next question we have. So this VH at an neutral null points is on the equatorial line. Okay. Next question we are moving ahead. Null points are on the axial line of a bar magnet when it is placed such that it's south pole points. Okay. South, east, northwest. So this is happening. VH null points happening towards right towards the south pole should point north. The south pole should point towards north. So B equal to BH at null point and null point is on the axial line. Null point is on the axial line. Next question we are moving ahead to like force of extent M1 and M2 are at a far distance apart. The energy required to bring them are not as so basically what we are talking about energy. So what is the formula for energy? All of you should know this is the formula for energy. You don't know for M1 M2 by R. You don't know for M1 M2 by R. This is easy question. Very easy question. Very easy question. If you know, you know. You don't know, you don't know. Yeah, next question we are going with the restoring couple for magnet oscillating in the vibration magnetometer is provided by. So restoring couple for magnet, restoring couple for a magnet oscillating in the vibration Magnetometer is provided by by horizontal component of Earth magnetic field gravity. Shows in this planet thread magnetic blah, 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 blah. So basically what a horizontal component of Earth magnetic field. Horizontal component of Earth magnetic field. Next questions we have that vibration magnetometer works on the principle of torque acting on the bar magnet and rotational inertia. Force acting on the bar magnet and rotational inertia, both the force and torque acting on this, and this is neither force or torque. The correct answer is vibration magnetometer works on the principle of torque acting on the ball magnet and rotational inertia. Next question, we're moving with a magnetic needle suspended by a silk thread is oscillating in the earth magnetic field. If the temperature of the needle is increased by 1500 degrees Celsius, then the time period increases, the time period increases, the time period remains unchanged, the needle stop vibrating. So what is happening here? See, as the temperature increases, the magnetic moment decreases. As the temperature increases, the magnetic moment decreases, and as the magnetic moment decreases, time period increases. As the magnetic moment decreases, time period increases. Do you agree? So as the magnetic moment decreases, time period increases. 2 pi, maybe so time decreases, time period increases. So I hope all of you understood this all the concepts. Okay, till then, thank you, bye bye. See you, check. Everyone.